Hey everyone, welcome to This Explainer. Okay, so today we're diving into something I find actually really satisfying. We're going to take your classic, maybe kind of scary looking textbook physics problem, and we're turning it into a totally logical, solvable puzzle. If you love that little aha moment when a giant jumble of parameters just suddenly clicks into perfect focus, well, you're absolutely in the right place. Let's crack this microscope code.
Section 1, the Optics Challenge.
Okay, let's dive right into this. You know how physics word problems just love to hit you with this massive wall of text right out of the gate? It can definitely feel a bit intimidating, but hey, we're going to be systematic about this. Let's look at the raw, unedited challenge exactly as it's written in the source. It says, a microscope has an objective of focal length 2 centimeters, eyepiece of focal length 4 centimeters, and the tube length of 40 centimeters. If the distance of distinct vision of eye is 25 centimeters, the magnification in the microscope is, and then boom, we get our four options. 100, 125, 150, or 250. Now, I don't know about you, but when I first scan a paragraph like that, my brain just immediately zeroes in on all the jargon. It's like alphabet soup. We've got focal length repeated, we've got tube length, and what in the world is distance of distinct vision, right? It is a whole lot of data crammed into two really short sentences. But the secret here, the real trick to these things, is realizing that this isn't just a story. It's actually a super precise inventory list. All right, section 2, deconstructing the variables. So let's put on our detective hats and pull this thing apart piece by piece. Our very first clue, right there in the text, is the objective. Specifically, the objective of focal length 2 centimeters. We're going to go ahead and call this variable f sub o. Now, in a real microscope, the objective is that little lens right down at the very bottom, literally the closest one to the tiny thing you're trying to look at. And its focal length, that 2 centimeter measurement, just tells us exactly how strongly it bends the light right at the source. Moving right on up the microscope, we hit our second piece of evidence, which is the eyepiece. The problem gives us an eyepiece of focal length 4 centimeters. We'll naturally call this one f sub e. And I mean, just like the name says, this is the lens up at the top where you physically put your eye. It's got a slightly longer focal length of 4 centimeters, and its whole job is basically to take whatever that first lens did and just push the magnification even further. Next up on our list, we've got the tube length of 40 centimeters. Let's just label this guy L. I actually love this variable because it is so incredibly easy to picture. Just imagine the actual metal body of the microscope itself. That 40 centimeters, that's the physical space, the actual tunnel separating our 2 centimeter objective lens at the bottom from our 4 centimeter eyepiece lens at the top. The light literally has to travel all the way through that 40 centimeter gap. And finally, we hit our last variable. Honestly, this one is kind of fascinating because it has absolutely nothing to do with the microscope itself. The text mentions the distance of distinct vision of eye is 25 centimeters. Let's call this D. This is actually all about us, the human observer. 25 centimeters is the standard measurement for the closest distance a normal human eye can focus on something comfortably without straining. Microscopes are literally engineered around our own biology, designed to project that final image right at this 25 centimeter sweet spot. So the crucial point is, look what we just did. We totally tamed that scary opening paragraph. We smoothly transitioned from a big, dense block of textbook text into a super clean, organized inventory list of just 4 numbers. We've got an objective at 2, an eyepiece at 4, a tube spanning 40, and a human eye perfectly happy at 25. Now we are totally ready to tackle the math. Moving on to section 3, the two-stage amplifier. Okay, before we just start blindly plugging numbers into a calculator, let's think about the actual physics here for a second. Think of a compound microscope exactly like a two-stage amplifier. It doesn't just magnify the image once, no, it's a total tag team effort. Stage 1 is that objective lens down at the bottom. It grabs the tiny object and makes an initial magnified image right inside that 40 centimeter tube. Then stage 2 steps up. That's our eyepiece. It looks at that already magnified image and acts like a magnifying glass for it, blowing it up a second time before it ever even reaches our eye. So to find the total power of the whole shebang, you just multiply the power of stage 1 by the power of stage 2. Which brings us to section 4, the magnification formula. Now, I know equations can look like a chore to memorize, but this one, it's basically a magic key, and it brilliantly illustrates that two-stage amplifier concept we just talked about. Look at how it's built. Total magnification, M, equals our first stage multiplied by our second stage. That first bracket, L divided by f sub o, that's the muscle of the objective lens.
the tube length divided by its focal length. The second bracket, d divided by f sub b, well, that's the power of the eyepiece, our distinct vision distance divided by its focal length. Literally all 4 of the pieces we just collected fit perfectly into this one elegant equation.
All right, section 5, calculating the solution.
Okay, let's actually run the numbers. We're going to do this in 2 really satisfying halves. Step 1, let's figure out our objective multiplier. We just take our tube length, which is 40 centimeters, and divide it by our objective focal length, which is 2, and 40 divided by 2 gives us 20. Simple enough. So that first lens at the bottom is making the image 20 times larger. Now, step 2, the eyepiece multiplier. We take our eye's distinct vision distance, that 25 centimeters, and divide it by the eyepiece focal length of 4. 25 divided by 4, that gives us 6.25, which means our eyepiece takes that 20x image and blows it up another 6.25 times. Let's move to the next stage and see how this all builds up. We've got our 2 multipliers ready to go, 20 from the objective and 6.25 from the eyepiece. Our formula says we just need to multiply them together for the grand finale. So 20 times 6.25. If you want to do it in your head, well, 20 times 6 is 120, right? And 20 times a quarter is 5, so 120 plus 5.
So what does this all mean? Considering every single parameter we painstakingly pulled from that first paragraph, what is the final, absolute, total magnification of this compound microscope?
125. The microscope magnifies the original object exactly 125 times. I mean, look how smoothly that worked out. We literally took a dense, confusing block of text, pulled out the exact right clues, used the 2-stage amplifier concept, and landed beautifully on a nice, clean, whole number. Seriously, there is nothing quite like the dopamine hit of perfectly cracking the math.
Looping right back to our original challenge image, we can confidently confirm that our hard-earned answer of 125 is a perfect match for option 2. Case completely closed, my friends. But hey, before we wrap up this explainer, I do want to leave you with a little something to chew on. We know exactly how this machine works now, right? We know the variables. But imagine you're the engineer. If you wanted to double this magnification, say you wanted to hit that 250 mark in option 4, which single variable from our list would you try to change first, and why? Think about how tweaking the tube length or maybe swapping out a lens would completely shift that final multiplier. I highly encourage you to go play around with the formula yourself. Thank you so much for joining me as we deconstructed this puzzle together. Keep questioning, keep learning, and I'll see you in the next explainer.